What if I told you that the simple gut instinct you use to solve a number puzzle is the exact same logic that powers every single computer on this planet? Well, today we're going on a code breaker's journey. We're going to start with patterns you already get and follow them all the way into the heart of a machine.
So to prove you're already a natural-born codebreaker, just look at these sequences. Take a second. Can you figure out the next number in each one? I bet you can. That first one? Well, you're just adding 2 each time, right? So the next number is 11. The second one? Same idea. Gives you 12. And that last one? That's the famous Fibonacci sequence. You just add the 2 previous numbers to get the next one, which means the next number is 13.
See, you've already got it. That instinct you just used, that spark of recognition, that's exactly what we're going to formalize today. We're going to give that instinct a language.
So what is a sequence, really? When we get right down to it, it's just a bunch of things, or elements, arranged in a very specific order. Each element has its own precise position, its own index, kind of like a series of labeled mailboxes. The first one is A1, the second is A2, the third is A3, and on and on.
And you can break down any sequence by looking at 3 key things. First, it has a specific order. Second, it has bounds. It can be finite, with a clear end, like the letters in your name, or it can be infinite, like all the odd numbers, just going on forever. And finally, its elements. The actual things in the sequence can be totally unique, or they can be repeated.
Okay, so if we want a machine to see these patterns just like we do, how do we actually code them? How do we write a rule that lets us predict any step in the journey, even one way down the line? Well, it turns out there are 2 main ways to do this. The first way is what we call the recursive loop, and I love this visual. It's like a factory conveyor belt. To get the next item, you have to look at the previous item and do something to it. In this case, you take whatever number came before and just add 4. But here's the crucial part. You have to have a starting point. You need that first item, like A1 equals 2 right here, to kick the whole process off.
Now, the second path is the explicit arrow, and this is a total game changer. It's a direct shot. You don't need to know the 9th term to figure out the 10th. No way. You just plug the position you want, in this case 10, straight into the formula. It's incredibly powerful and way more efficient.
The best way to think about the difference is with a metaphor. The recursive path is like taking stepping stones. You have to hit every single stone one by one to get to your destination, which is fine for a short trip, but awful if you need to find the millionth term. The explicit path, though, that's a teleporter. It zaps you to any term you want instantly with just one single calculation.
And these 2 methods are the engines behind the 2 most common types of sequences. You've got your arithmetic sequence, which grows nice and steady because its engine is just simple addition. But then you have the geometric sequence, which absolutely explodes because its engine is multiplication. You can literally see the difference in their graphs. One's a straight line, the other is a curve that shoots for the sky.
Okay, get ready, because this is where we take the big leap. This was never just about numbers. We're now at the point where we can actually translate a human thought into pure, cold machine logic.
First things first, we got to expand our thinking. Sequences aren't just for numbers. A word is just a finite sequence of letters. A sentence is just a sequence of words. This whole idea of ordered elements applies to all sorts of data arrays.
Now, really pay attention to this next idea. This is the moment it all clicks. This is the moment the abstract becomes real. This is literally the birth of machine logic.
And this right here is the key, the characteristic function. Think of it like a bouncer at a really exclusive club. It looks at an item and it asks one simple question. Are you in my set? Are you on the list? If the answer is yes, it spits out a 1, which you can think of as true or power on. If the answer is no, it spits out a 0, false or power off. And just like that, an abstract idea like belonging to a group gets translated into a simple, concrete number.
And here's the magic. Because we're now just dealing with simple 1s and 0s, we can use basic arithmetic, the stuff you learned in grade school, to build the fundamental logic that powers every computer. Concepts like AND, OR, and XOR stop being fuzzy ideas and become simple, clean math formulas.
I mean, look how elegant this is. Multiplication becomes a perfect logical AND gate. For the function to give you a 1, a true result, an element has to be in both set A and set B. Why? Because the only way to get a 1 when you multiply is 1 times 1. If either of them is 0, the whole thing becomes 0.
It's beautiful. It has to be in both.
And then, just by sprinkling in a little addition and subtraction, we can build the other gates. The formula for or a union, makes sure you count everything in either set, but you don't double count the stuff in the middle. And the formula for XOR creates that really strict either or, but not both condition by subtracting out that middle overlap twice.
Okay, let's bring this all home. In this final section, we're going to see how this all comes together. We're going to connect the code that we've just built in our minds to the actual physical architecture inside our machines.
And here it is. This is the aha moment. This is why we learned all that math. That characteristic function, it's the bridge. It's the translator. It takes a human-readable array, like the word discrete, and turns it into a binary string of machine data that a computer can actually store and process.
And the process is just so stunningly logical. First, you set up an ordered sequence, like an alphabet for your data. Step 2, the characteristic function scans your specific data, and for each spot in the alphabet, it asks, is this letter here? It assigns a 1 for yes and a 0 for no. And the result? You get a permanent binary string that is a perfect representation of your data.
Let's look at one final super concrete example. In a 6-bit system, the number 15 isn't just a symbol. It's a physical sequence of on-off switches, 001111. The characteristic function has literally mapped its value onto a physical binary state. The thought has become a thing.
So, after all that, after going from a simple number puzzle all the way to a complex silicon chip, what did our journey really reveal? What's the big takeaway here?
What it all comes down to is this. Sequences are so much more than just math puzzles in a textbook. They are the fundamental language. They are the Rosetta Stone that allows our abstract human logic to be physically written into the architecture of a machine. From our own pattern-seeking brains to the apps running on our screens, it all starts with a simple, ordered line.